Okay, so hello everyone. Welcome to today's Build Environment talk series. This seminar series is co-organized by Center for Housing and Urban Development, GeoSat, Center for Geospatial Science, Applications and Technology, and Design and Analytics Lab for Urban Artificial Intelligence at Texas A&M. So today we have our speaker, Tyler, here to give a talk about controlling for spatial confounding and spatial interference in causal inference. So without further ado, Tyler, the floor is yours.
Cool. Thank you, Justin. And really, it's a pleasure to be here. Thanks for inviting me, and really excited to talk about some of this work that I've been doing in conjunction with my advisor, Peter Kedron, here at Arizona State University. So to begin, I'll just motivate briefly why we care about causal inference. And what the heck do I mean when I talk about causal inference? So at the end of the day, in every statistical analysis, our goal is to deduce causal relationships through statistical models. But statistical models present opportunities to infer associational relationships. So we analyze how correlated two variables may be, or a set of variables may be. And we can measure the strength of these correlations, but these statistical models don't offer the ability to assign causal interpretations to parameters or relationships between variables. And it's really important that we know these things so that for built environments students and researchers and policy analysts can understand what drives certain phenomena and can make principled interventions to target certain objectives. So if you know what is causing a phenomenon that you want to influence, then you know what dial you can turn or what policies you can implement to change things. But space and the distributions of variables in space present unique challenges during this process, and those are primarily scale, confounding, and interference. I include scale here because it's a uniquely spatial problem, and it's the subject of a lot of research in spatial analysis, GeoAI, GI science, but this talk is primarily going to focus on confounding and interference. So there's the need for a meta-analysis of use cases among a lot of different existing spatial causal models. Lots of these things exist, they're out there, but there's not really that sort of guidance that we have for non-causal spatial models that allows us to so easily whip up a spatial regression to analyze something in econometrics, or analyze a policy do a policy evaluation using GeoAI. And we know we have good guidelines for how to do these things in non-causal spatial statistics, but we need to extend that sort of guidance to causal spatial statistics. And before I keep going, I just want to say, please feel free to stop me at any point with any questions. I'm more than happy to answer them mid-presentation, especially if there's something on a slide that you don't understand or that comes to mind. Please just let me know. So now that I've set that up, our objectives for this research were twofold. First, we wanted to demonstrate that intuition from non-causal spatial modeling, so the spatial statistics of the 80s and 90s, this is like Luke Anselin's heritage, sort of Lesage, Pace, etc. That this intuition holds in causal spatial modeling. So we want to carry the guidance that we've already built up into a new setting, into this causal setting. And secondly, we wanted to develop a more standardized code base for spatial causal models. And the two of these together, the ultimate goal is to make these sorts of things more readily usable for end users, for policy analysts who maybe don't know maybe don't know as much mathematics or aren't as experienced with programming and are not homebrewing these models themselves. We wanted to package them up, make them easier to use, and hopefully get their application more widely available. So what do I mean when I talk about causal inference? Let's get into the details. So ideally, we have a treatment variable z measured at locations I, and we have an outcome variable y also measured at locations I. Excuse me. And in this ideal scenario, we can measure the impact of z on y directly by setting the two variables up in a regression type format and inferring the strength of that relationship. If nothing else is going on, and we know that z directly affects y, we can get an estimate for that parameter, and we can give that parameter a causal interpretation. We can say that z probably causes y up to some confidence level and with a certain magnitude. Similarly, or sorry, the challenge comes in when we have this third variable x. So if there's a third variable x also measured at locations I, and if x affects both the treatment variable and the outcome variable, then x is called a confounder. And the issue with this is that now not all of the causality to y flows through z. Z only contributes to some of y, but some of y is also contributed by x. And z depends on x as a result. And so this is confounding. This is a variable that is affecting both our treatment variable and our outcome variable, and it's going to bias our inferences and alter our inferences, making them incorrect if we do not condition on it in our regression. Regression is the prototype for this stuff. In principle, you could use anything, but we'll talk primarily about linear regression. So what's an example of this? So suppose that our locations here are United States. Our outcome variable y is drunk driving crashes, and our treatment is z is the drinking age in the state. So perhaps if the drinking age is over 21 or under 21. Our non-spatial confounder here might be the number of cars. So if the number of cars in a state, if we didn't know the number of cars in the state and we didn't have any information about it and we didn't think that it affected the number of drunk driving crashes, we would be able to directly measure the influence of drinking age on drunk driving crashes in a state. But if we do think that the number of cars might raise the number of drunk driving crashes purely because there's more cars on the road, then we might have a non-spatial confounder, and we might represent that system like this, where the number of cars on the road both influences the number of crashes and the number of drunk drivers on the road. And so if we don't condition on the number of cars, we will not have valid inferences. So the crucial idea here is that conditioning on xi, so including it in a regression, permits inference on the treatment effects zi arrow yi. It removes that green arrow and forces all of the quote unquote causality to flow through the treatment effect, flow through z into y. So the challenge in a spatial scenario is called spatial confounding. Non-treatment variables here may contribute to the outcome through spatial relationships. So if we have, take the same example, these three states, A, B, and C, hypothetical states, we have information on drunk driving crashes in each state, and we have information on the drinking age in each state. But there may be more bars in state B than in state A. And even if state B has a higher drinking age or a lower drinking age and more bars, then people in state A may drive over to state B to go to those bars and then drive back across the border and crash in state A. And so this is an example of a spatial confounder, where the presence of where the value of a variable in one location influences the treatment and the outcome variables in another location. This is a sort of spatial spillover effect that can severely bias inferences. Graphically, it looks like this. We have a spatial variable measured at locations I here, and the spatial variable is measured at locations j here. And now you see the confounding variable xi affects the treatment and the outcome variable at location j, and vice versa for xj. So here it's the number of bars at location I is influencing the drinking ages at location j and the number of drunk driving crashes in location j. And that sort of a spillover requires us to condition now on our neighbors' confounding variables, not just our own confounding variables. The other issue that comes up in spatial analysis is spatial interference. So if units influence each other's responses to an intervention, then we cannot isolate the effect of that intervention. So here, in the same drunk driving example, the interference may be the drinking age of neighboring states. So perhaps voters in state A lower the drinking age to be 18, but voters in state B see that drinking age is 18 over in state A, and they say, we don't want it to be that low. We're going to keep it at 21. That's an interference effect. They see things happening in state A, they perceive something, and they alter their treatment variable, the value of their treatment variable at that location as a result. And this causes problems in interference again, because we can't isolate the effect of a given intervention in a given location. There's multiple effects from one intervention that's spread across space. And for those of you inculcated in the GI science literature, this is related to Tobler's first law. So nearby things tend to be related. If some action at state B is probably likely going to affect states A and C. Graphically, again, this looks like the graph on the right. So spatial interference is when the treatment variable at location I affects the outcome variable at location J, or vice versa. Here, the drinking age in state A may cause there to be more drunk driving crashes in state B, if the same idea happens as I was talking about earlier, that there are more people going across the border to state A to drink and then coming back and crashing in state B. So, did I skip one? Okay. So there are a bunch of different kinds of spatial causal models out there. There are a lot of different ways to correct for this and condition on non-spatial confounders and spatial confounders, and to adjust for interference effects. Some are listed here on the screen. For our purposes, we're focusing primarily on spatial regression adjustment. So none of these, it's the second option here, where we add something to the regression equation that can allow us to condition on or adjust for confounding or interference variables. But we include these for completeness, and ideally, in the end, all of these will be implemented in the module, so that to provide one sort of unified interface to approaching spatial causality. So to precisely and mathematically, to adjust for spatial confounding, we use a conditional autoregressive model, or a CAR model. I'm going to refer to this as a CAR model. There's a bunch of math up here, but the idea is that we model the spatial confounder as a normal variable with a specified covariance matrix. The covariance matrix depends on a spatial, has spatial structure encoded in it via this W. W is a weights matrix that can reflect the influence of neighbors on each other when measuring that spatial structure. We'll see some pictures of this later. So our strategy is we include this unobserved variable that has a spatial structure that along the lines of which we think the spatial confounding follows. And by adding that into our model, we can condition on this unknown spatial confounding and isolate that arrow from Z to Y. For spatial interference, the adjustments are a little simpler. They're simply adding a lag of the treatment variable. So if we think that the spatial interference follows a spatial structure with, described by the matrix W, we can incorporate a lag of the treatment variable WZ into the model, and this will properly account and average for the spatial spillovers. So this is an image here. If we think that these green squares are Z equals 1, and they have a treatment, and these black squares are Z equals 0, they don't have a treatment, then this sort of adjustment here, and this describes a spatial weights matrix that weights each of the neighbors by 1/4 and incorporates these 4 neighbors, rook neighbors, into the averaging. So the variable here, the averaged WZ variable here would be 3/4, 1/4 plus 1/4 plus 1/4 plus 0/4. So we incorporate a spatial lag of the treatment variables to account for their effects on each other. To analyze and develop guidance for modelers and to see how well our guidance transfers into into the causal setting, from the non-causal setting into the causal setting, we designed a simulation study. And the parameters of interest were twofold. We were interested in varying the structure of the spatial confounding and the spatial interference in data, and seeing how that squared up against the structure of spatial confounding and spatial interference in the model. And so if we wanted to see if we match or we mismatch the structure of confounding and interference in the data versus the structures in the model, what happens when those exactly match, when those don't match, and how well do different models perform on different varieties of spatial confounding and interference. Excuse me. To do this, we considered 4 different kinds of weights matrices. None, so this is no spatial confounding or no spatial interference. Binary weights matrices, so you are a location is related to its neighbors, its immediate neighbors, and its immediate neighbors only. distance-based weights where a location is dependent on its neighbors up to a certain distance away, and region-based weights. So region-based weights are you are dependent on all of your neighbors within a given region. And this is interesting because these are sort of equivalent to fixed effects, and there's some interesting literature on these in like Hodges and Reich 2010, and Anselin and Amaral have a paper on them about when you should use these sorts of region-level fixed effects and when you should use spatial lags. So we were particularly interested in these. And you can already see if our spatial domain is this lattice and these are our 4 regions, if we perhaps use these 4 regions in our model, but the true spatial structure is distance-based or binary, then we're going to have problems at these discontinuities here, these differences between areas, because this location here, and according to the region-based weights, is related to all of these locations, but it's not at all related to its neighbor across the border. And that causes a mismatch if we use one in the data and one in the model. So we'll see that play out. So all told, there's 16 total data scenarios. So these 4 weights matrices for confounding, and these 4 weights matrices for interference. Multiply 4 by 4, and you get 16. For the models, we used a OLS, so an ordinary least squares, a standard linear regression, a CAR model, which is that conditional autoregressive model with the spatial structure that I was describing, and a joint model for the propensity score and outcome. The propensity score is the probability of treatment. So we include the probability of a unit being treated into the model to model the treatment variable as a function of confounders. And this can allow us to condition on confounders potentially better than and to incorporate different spatial structures into the model in a different way. So again, to reiterate, our research objectives here are to analyze how non-causal spatial modeling guidance transfers to a causal model, and simultaneously to develop this standardized code base. So to accomplish number 1, we designed a simulation experiment that analyzes relative performance of spatial causal models. And to facilitate that experiment, we designed this code base as well. So for OLS cannot account for spatial confounding. There is no confounding adjustment present in it. So the one confounding adjustment, so called here, is no confounding adjustment in the model. And for CAR and joint models, we add the 3 confounding adjustments, which are the ones where confounding is present. CAR and the joint models must model spatial confounding. We also applied 4 different interference adjustments because those were applicable for all models, and these were the 4 weights matrices that I described earlier. So all told, this gives 28 total models, and we ran those on 16 different data scenarios each for a total of 448 combinations on this big model and data matrix. So let's take a look at these results. So this is a really big figure. We're going to walk through it slowly. On the left panel, you see here, panel A gives a ratio of bias to effect size. The entire goal here is to analyze how well we're capturing the treatment effect, the effect of the treatment variable on the outcome variable. Panel A shows the bias in that estimated treatment effect. So how different the estimated treatment effect is from the true treatment effect. The other thing that we incorporated here was we divided this by the true treatment effect. So in the end, to obtain a ratio between the error and the true effect. So this is on a scale of like 0 to 1.4 or so. But you can imagine if the value is 1, then that means that the error in our estimated treatment effect is about the same order of magnitude as the treatment effect itself. So this means we have a very high level of uncertainty present in our estimates. On the other panel, you see we have the log of the variance. So that we estimated all of these in a Bayesian setting, which means that we have full posterior distributions for all of the parameter estimates. So the log of the variance here is the log of the posterior variance for the treatment effect. It's a measure of how uncertain we are of our estimate. So A is how imprecise our estimates are, and B is how inaccurate our estimates are. We use the log of the variance because the variances were all quite small, and we wanted to pretty much just show relative orderings. On the x-axis, you see here we have data scenarios. So N stands for none, B stands for binary, D for distance, and R for region. These are the different weights matrices. And these are grouped primarily by confounding. So the first 4 columns here are no spatial confounding with 4 different kinds of interference, and and so on. On the y-axis, we have our different models. So the x-axis is the data scenario, the y-axis is the model, and these first 4 columns are ordinary least squares, where we're trying to capture the data scenario, the data using an OLS model. The next 12 are the car model, and the next 12 are the joint model. So these models get more and more complicated as we go down the y-axis. And the OLS is a pretty straightforward model. The car model starts to get more complex, and the joint model involves multiple car terms in order to more flexibly analyze spatial structure. And so just from looking at the right plot here, we see that the log of the variance of our posterior variance of our treatment effect increases generally as we go down the plot. And that very simply says that we're getting more and more inaccurate, or more and more imprecise in our estimates, because our uncertainty around the true treatment effect is growing as we go forwards. The next thing I wanted to point out is that in the case where there's no spatial confounding, that we should, generally speaking, prefer CAR to OLS, even if there is no true spatial confounding in the data. The CAR model has relatively low bias on all of these no spatial confounding scenarios, and has moderate bias, but less overall than the OLS model on scenarios where there is spatial confounding. So it looks like the CAR model does a pretty good job of mitigating the effects of spatial confounding in the data, and allowing us to condition on those and isolate the treatment effect. That's the entire goal. It also has relatively low variance, and especially has low variance in the scenario where there's no spatial confounding at all. So this indicates that it properly degenerates to a non-spatial model in the case that there is no spatial effects. Similarly, we indicate that you should prefer a joint model over a CAR model if it's more likely that spatial issues are present. So if you have a stronger degree of belief as a modeler that there are spatial confounding or interference in your data, the joint model will give you lower bias overall. However, it's more complicated. So you're going to sacrifice variance as a result. Your estimates will be less precise, and you'll have more parameters to make. And that's sort of the trade-off, is that you get potentially more accurate estimates, you get closer to the true value, but your potential error on that is a lot wider. Your confidence intervals, or here in the Bayesian setting, credible intervals, are going to be wider than in other models. The next thing we wanted to mention is that region-based weights have sort of limited or perhaps more restrictive use cases. So remember what I was saying earlier about those discontinuities at the boundaries of the regions. We see that manifesting here pretty clearly. If you have a region-based weights matrix in the model, but the data confounding does not follow a region-based weights structure, then you may suffer from extremely high bias. And and this is because if the region-based weights matrix in the model is a really restrictive assumption, and it's putting that really restrictive assumption on data that doesn't follow such an assumption. And as a result, you lose out a little bit, and you misspecify your model, and you gain high bias and high variance as a result. So it's very important to be vigilant for these. However, if the true confounding structure is region-based, you have very low bias in both of the spatial models, because you've modeled the spatial confounding in the data correctly, and your inferences are valid. But a priori, you never really know. So these are different plots. These are two sort of groupings of the data into matched and unmatched scenarios. The matched scenarios are scenarios where the data, spatial confounding, and interference exactly matches the spatial confounding and interference in the model. And the unmatched scenarios are everything else. But you see here, if we bin all of those bias to effect size ratios, and we bin all of those log variance values by these matched and unmatched categories, we don't really see much of a difference. So overall, it's not like unmatched scenarios have dramatically higher bias, although they do tend to have higher bias a little bit. On average, most of the unmatched scenarios are about the same, have about the same level of bias as the matched scenarios. And so this is a really big problem. It means that a priori, you're never going to know if you got the spatial structure right. And that, I mean, that's something that spatial modelers deal with all the time, that policy evaluation deals with all the time. But it's very important to be cognizant of, because you have to, you really need to use post hoc diagnostics to analyze whether or not your model is fitting properly. The thing that is missing from this plot, and purposefully so, is that most of the unmatched scenarios hit convergence flags and other issues during the fitting procedure that indicated that the posterior chains were not converging to a steady state distribution. And this means that our inferences were probably not as, it could be indicative of sampler issues, but we tuned the samplers a good deal, and it's likely issues indicative that our models were not fitting well because they didn't capture the data correctly. So you really need to use these diagnostic flags. About 64% of the unmatched scenarios hit them, whereas much fewer of the matched scenarios hit these flags. But they can really give you a lot of insight under the hood of what's happening inside these samplers. So to reiterate, the 5 principles that we evaluated from the non-causal setting into the causal setting were first, to prefer less complex models, but if there's a possibility of spatial issues, to prefer a CAR model. And if there is an even stronger possibility, if you're very sure that there is both interference and confounding, to prefer a joint model for the treatment and the outcome variables. Ideally with the binary confounding adjustment, because those perform the best in general. 4 is for be vigilant for region-based weight use cases. If it's the relevant type of spatial structure to study, then use it by all means. But if it's not, excuse me, it's very important to be principled in the inclusion of these in your model. And 5, use post hoc diagnostics, because they can illuminate issues in the model structure that you may not otherwise see. So some of our key lessons here. First off is that there's just so many of these spatial causal models out here, and we only focus on a really small subset. But the proliferation of new models in GI science, we see this in GeoAI as well, it spurs the need for this sort of meta-analytical research, where we're taking a lot of these models and we're condensing them down. We're saying, how can we compare these? What are their relative performances? What are their relative use cases, different assumptions they rely on, and when are they applicable? And so we aim to do that in this sort of synthetic research, where we take a lot of different models and bring them together to see what happens. This also illustrates the value of working with domain experts on spatial problems. So a priori, you never know which of these different kinds of models are more relevant. But if you're working with a domain expert, they may know which kind of spatial structure is most applicable for your problem. Our next steps include expanding code base, developing tutorials, and creating more documentation. So that's a work in progress right now. And you can see our Python package and the simulation data that we used at my GitHub site. I just wanted to point you to it. So there's some of this exists now. We've got a few tutorials up, and the documentation is coming as it goes. So, and this is the exact. So the other thing is that this package is what we use to run these simulations. So if you want, you can use this package directly and recreate all of our simulations. Cool. So that's about it. If there are any questions, I'm more than happy to answer them. Thank you for having me.
Well, wonderful. Thank you for giving us this talk. This is really a great experience to learn those spatial causality and causal and spatial confounding issues. Let me first check if there are any questions from the audience. Okay. I have some questions. So you talk about spatial confounding. You have the CAR model and the ONS model. What's the hypothesis difference for those two models? Can you use
Yeah, so in an OLS, the assumptions of an ordinary least squares model are that you can directly relate your treatment variable to your outcome variable, and including some non-spatial confounding variables to isolate that relationship. The CAR model incorporates a spatially structured error term that aims to soak up some of that spatial confounding that is present in the residuals of a model. And so by incorporating this spatially structured term, we condition on this spatial confounding that's happening in the data, subject to a certain weights matrix that we add. So it is actually, I wanted to include this picture. The CAR model is actually a fairly restrictive model, and you can kind of think of it as being able to model the strength of the presence of a given spatial structure in your data. So here, these dots are locations where, say, some event happens. Maybe they're cases of COVID, and these little regions around them are areas where there might be a raised probability of new COVID outbreaks because someone has COVID in those locations. The rho value here is a parameter representing the strength of that intensity. So you see that these fields get stronger and stronger as rho increases. A CAR model does exactly this. It estimates the value of rho for one of these spatial structures, on sort of a sliding scale, but it can't adaptively adjust that spatial structure. So it takes a prescribed sort of thing like this. This is Queen weights matrix, binary adjacency matrix, and will tell you how present that structure is in the data, and that's it.
And how I remember in your illustration there is a U unknown. How is the U reflected in the CAR model?
So the U is the CAR model.
Oh, okay.
So this is a U. It's drawn from a multivariate normal distribution with this specific covariance matrix, and it's just a CAR model is an OLS model plus this additional U term, and this prior on the U term is what allows us to infer spatial structure in it.
Okay, makes perfect sense to me now.
Go back to the end.
Let me check if there are any.
Yeah.
So seems our audience also think your presentation is pretty clear. Okay.
Yep.
Yeah. From I don't know. Generally, for our audience, they might you have that in your future research. They like to see some real cases. So
yeah,
hopefully we can see that in the future.
Yeah, there's a lot of application work out there with different spatial causal models, and I'd be more than happy to point anyone to them. Lots of great work out there in these application areas. Our work here obviously is a bit of a more meta-analytical question. Excuse me, but I've used these in practice, and really they're not as difficult as you may think to use. I think the main thing that they do, that spatial causal models add, is they force you to think critically about the assumptions that you're imparting on your model, and how those will trickle down into your inferences and what they'll do to your inferences. So yeah, that's some of the most value. Yeah.
I'm also doing, so I just came up one case. I have a business competition and cooperation research, assuming that POIs, they compete or cooperate with each other with certain regions. So like you compete with your neighbor restaurants. So I think those are also some cases for spatial confounding and spatial causal, because they have the spatial relationship, and they have you can imagine there would be like they compete for customers, and their logistic like also have some spatial pattern in it. Yeah, and well, Tyler has this statistical model, SPAR and OAIS models. I do graph neural network. So from network science perspective to understand those things, I think these are two different angles and they may converge at some point.
They do, I think, actually. There's in non-spatial causal inference, there's a whole field of causal machine learning where people use neural nets like this, and not nearly as sophisticated neural nets as what you're talking about, to estimate treatment effects. And the idea is that if you have all the variables that you need to condition on in your model, you don't care about your model being interpretable as long as you can get the treatment effect. You're only isolating the treatment effect, and so you can use a neural net to do that, or a tree. There are certain tree structures like BART that allow you to do this. So it's really cool. And actually, I've been like wondering if you could use spatial neural nets instead of the non-spatial neural nets that people usually use. So that's a perfect example of where thinking spatially about causal inference can really add a lot.
Yes, that's really interesting. Okay, we are about time, and if there's no questions, I'm gonna end the recording. And thank you all for joining us today.